So I'll give you a little bit of an overview of the design of the new D29, which has been specifically built to profit of the new fourth generation source, synchrotron source that has been built with the upgrade of the ESRF. So let's see if I can put the pointer, otherwise it's probably here. No. Yeah, I guess you can see my mouse. Okay. So I'm going to show a characteristic of what is the new sources and what is achievable to the new sources, along with the goals in your beeline, a bit of the beeline layout performance, as I think that in the audience there might be some, let's say, light sources people, a bit of the versatile sample environment, and a bit on the data reduction and data sorting that we apply on the fly to make user's life a bit easier, and a bit of some results and future perspective. So of course, one of the initial goals for the beeline for constructing the D29 beeline was to resume and revamp the implication of using room temperature crystallography, which, as we all know, is better suited to reveal physiologically relevant conformation, which can usually be hidden when working at cryo temperature. So then present a better description of the thermal motion, which is closer to native and physiological condition again, in order to get a better understanding of the structure and potentially reveal the studies of ligand interaction also for the developing of new targets. Of course, because of the nature of radiation damage, serial crystallography is a good approach in order to overcome radiation damage issues and revealing the structure at room temperature. Of course, in addition on this, and as we all know from the initial experiments that were done in the last decades, a bit more than a decade, at free electron laser, working with microcrystals has also the distinct advantages that when you want to work with photoactivatable molecules, you have a better penetration of the light probe, of the laser probe, in order to excite a larger part of the volume of the crystals, which sometimes is a bit limited in larger crystals because of the penetration depth. So this makes it possible to work with photoactivatable proteins, also to work with photoactivatable ligand, and this we can think also about using cleavable cage compound and activatable cofactors, and also possibly to work also with temperature jump by using short infrared pulses. On the other hand, working with microcrystals has also the advantages that diffusion into microcrystals when we are performing soaking experiment, it's much faster because of a much advantageous ratio between the accessible surface and the volume compared with large crystals. So this ligand mixing approach is a good strategy for exploiting drug binding, but also in crystals directly, enzymatic reaction and pH changes. Similar as what is happening at APS in the last couple of years, the ESRF has went to a major upgrade or redesigning the whole lattice, which has moved from a two-band achromat to a hybrid multi-band achromat, which has the direct effect of reducing the divergence and the emittance of the X-ray sources. So here you see a comparison of what would be the beam emitted with the old machine and with the new machine, which of course it is reflected immediately into an increase in the brilliance, which is at least by a factor of 30 in a typical energy range, which major advantages which are coming from higher energy experiment. So one of the idea when we started this project of the upgrade of 29 was that how we can best profit of this increase. And we saw that even with the old ID29, and this is something that has also been observed on the other MX line, just by upgrading the sources, that would have been reflected in again in flux at the sample position by roughly a factor of 10. But then we start thinking, can we do actually better than that? And by redesigning, completing the beeline and increase this gain. So in a very simple calculation, we could approximately say that on a microfocus beeline, which is built on a third generation synchrotron, usually we have a bit more than 10 to the 12 photons per second, which is usually for MX experiment is limited by the bandwidth, which typically with the silicon 111 micrometer, it's roughly 10 to the minus 4 delta E over E, which of course reflects a 10 kV in an energy spreads of about 1 eV peak to peak. So that means that if we want to generate an X-ray pulse or illuminate a crystal with at least 10 to the 10 photons, we need to have at least an exposure time of roughly 10 milliseconds. As I said, a similar beeline at the fourth generation synchrotron would at least have a gain on flux by roughly a factor of 10, which practically speaking reduce the maximum, the minimum exposure time just down to 1 millisecond, which is more or less also in the ballpark of what are the capabilities of photon counting detector. So the question that we start asking ourselves is that can we actually push that even further to, let's say, go behind what is going to be the time scale range that are achievable, that were achievable in the previous beeline. So of course, in that perspective, we were very much influenced by what Lowe beeline were already doing, and in particular ID9, and of course biocars. And we start thinking about, let's say, using what I call the pink beam trick. So by trying to get more flux by expanding the bandwidth. This, of course, has some practical limitation of difficulties is that in order to perform serial crystallographic experiment, we wanted to have that focus in the microfocus beam, and in that way to achieve a good spatial resolution. Means to be able to sample very small crystals and maximizing the signal to noise, and of course time resolution by reducing the exposure time. So back at the time when we were still drawing the potential optic of the beelines, we did a lot of simulation. At the time was with nanobrag to try to find a good compromise that we could increase the flux, avoid overlaps across the spots, and also the effect because of wanting to achieve a very high spatial resolution, what was going to be the effect of the divergence in the spots that were going to be produced by the diffraction. And of course, last and not least, also the kind of heat load that was going to produce both on the optics and on the sample. So by combining all this calculation, we end up to show that we could achieve, if we could achieve a time resolution in the microsecond time range, so to have shorter exposure in the microsecond time regime, that was going to be a good strategy in order to be able to sample all reactions that are occurring from the micro to millisecond time range, which happen to be a very interesting time scales for what for the vast majority of the enzymatic processes. Of course, that would imply that the detector that was using was not suitable enough to achieve that kind of resolution, and also to be able to achieve enough flux to make sure that we to obtain enough flux in that short exposure time. So from a beeline point of view, the goal, basically, we have found a good sweet spot in terms of bandwidth, which is 1%, which is typically, let's say, much narrower than what is used at Laue beeline, but still much larger than what is used in a conventional MX beeline. This is, as an effect, as has been also previously shown by other experiments in the past, of course, a thickening the UL's field. And so with when collecting data from stills to make it possible to measure more complete Bragg spots without rotation, which is, of course, the typical experiment that we do on serial crystallography experiment. Technically speaking, this is achieved with a multi-layer monochromator. So we have, as you see here, double multi-layer monochromator mirror with 3 different coatings. In like, I would say 90% of experiment, we use the 1% bandwidth, which is obtained with this palladium boron carbide coating. The titanium chromium boron carbide coating allows us to decrease this bandwidth to 0.4%, which is something that was we defined because it was at the time that we was designing very close to what is the spectral bandwidth at many free electron laser. And then we have an additional coatings which is initially designed to work at high energy. The whole system is mounted on an hexapod, and this was a very convenient solution in order to be able to, from the rotation around an arbitrary axis, which is placed on the surface of the first mirror, in order to change the energy. And by changing the height of the whole hexapod, allows us to change the stripes without avoiding basically a mechanical problem, which could come from stacking different tables on top of the other, and then get it less stable. Also considering that the monochromator is placed at around 30 meters from the source, but is basically 70 meters from the sample. So any kind of vibration and that we would observe at this stage will be clearly propagated by a larger shift at the sample position. And then, in order to reduce the exposure time, of course, as we said, if we do expect to have pulses in the range of the microsecond, because that will allow us to achieve, with the flux that we can achieve in this 1% bandwidth, we have a double chopper system. So we have a first heat load chopper, which is internally designed. You see this slots profile. This is produces 90 microsecond pulses by spinning, and we have by moving around the beam, or basically moving the chopper at different position relative to the beam, we can change different frequency of operation. Again, in probably in 99% of the cases, we always work at this 231 hertz. And then downstream, after the heat load chopper, there is a fast chopper, which has been developed by a Swiss company on our specification, which is a very small device, which is magnetic levitating. And here you see there are 3 different slots. So by aligning the chopper at 3 different positions, we can modulate the pulse length to be 10, 20, and 30 microseconds. Of course, since this is magnetic levitating, it's essential that we reduce the heat load from the first chopper in order to preserve the magnetization and avoid heating of the chopper itself. Both of them, they have a very low jitter, and allow us to make, let's say, very accurate reproducibility of the pulse, which is also very important from when we doing, as you will see in a minute, fixed target experiment. Downstream from the chopper, or from the 2 chopper, we have fast diodes. that we use to make sure that the pulse, the chopper is synchronized with the master clock. A master clock, and sorry, and this is, for example, this is the pulse which is produced when we have the fast chopper in, which of course selects a bit of the pulse that is produced from the heat load chopper. The whole experiment is synchronized with the radio frequency of the machine. This is not, let's say, an absolute requirement, at least not for now, because we are not separating the bunches like it's done at Laue beeline, because of course with the shortest exposure time of 10 microsecond, it's basically a bit more than 3 full ring turn at the ESRF, but still this provides us an absolute clock from which we can synchronize both the chopper and the experimental setup, and when using light probe lasers, and of course the acquisition of the detector. So this is done as I said, by propagating this clock which is produced by the machine, and this way we make sure that there is a sort of single point of truth or a single clock which is used by all the devices that are on the beeline. Sorry. So this is a bit an overview of the experimental setup. So I said we have 2 choppers. We can produce up to the maximum repetition rate of 925. And again, of course, it's this is like a strange number, or it's at least it's not a very round number, because it's an integer division of the frequency that is of the radio frequency of the storage ring, that can produce pulse X-ray down to 10 microsecond, which are focused down at the sample position, which is equipped with a newly developed microdiffractometer, which with this SSX fast head scan that you will see, I'll say a few more in the middle, and the versatile sample environment where we can also accommodate different kind of injector or other kind of sample delivery system, as tape drive, or also systems that are developed by the users that we can accommodate. The detector, since the pulses are quite bright and we cannot be a photon counting detector, so we have integrated a Jungfrau 4M detector developed by PSI, and of which we have developed, and I'll say a few words later on, a dedicated backend infrastructure that analyze the frames with containing hits on the fly. The system is also, we are commissioning a nanosecond laser, which can also illuminate, shed light at the sample position. And so this is an overview of a very close-up of the experimental setup. Here you have the vessel with the KB mirror. KB, it's a KB system with mirror with fixed curvature that is focusing down the beam to slightly bit more than 2 micron. It's actually 4 micron in the horizontal and 2 micron in the vertical. The beam is, as you can imagine, very hot, and this is the damage that we have produced. Nowadays it's much much worse condition of the BGO scintillating material that we have the sample position, as you see here, to identify the position of the beam. And since the detector is say a small surface detector, or in order to intercept higher angle reflection, we need of course to move very close, and the closest position is a little bit more than 100 millimeter of the sample. Is actually 103 millimeter from the sample. And here you see the microdiffractometer with this fixed target support, and that I'll show you a bit more in detail in the middle. So this is an overview of the whole beeline layout. So as I said before, we have two optic catches. The first optic catch, where is the multi-layer monochromator, is located. A second optic catch, which is the home of the double chop system. Then we have a long beam transfer line, and that brings the beam into the experimental hatch. And here you see again from the top. Next to the experimental hatch, there is a sample preparation laboratory with different bench spaces, which is also equipped with controlled humidity tent. And we have equipped now another surface with for light sensitive sample with different colored light sources. And we will install, we have received, will install an anaerobic glove box that will also be installed in the sample preparation lab. Both the experimental hatch and the lab are constantly controlled in temperature and humidity. And this is also has been very crucial because it has been very close to the Alps. Humidity, there is quite a bit of excursion between summer and winter. Okay, so this is just a real diffraction pattern, which is overlapping quite well what we had initially simulated. And in this case, we took a very large crystal in order to be able to see all the spots. And then, as you can see, the spots, they are a bit strict. And this is, of course, both an effect, I believe, of the divergence of the beam, because since we are focusing down to, we have a quite strong magnification, and also of the bandwidth. This, I think, it's actually providing a good help, as I said, because of making the spots less partial from when we collect from, okay, let's see, from still images. So in terms of sample delivery, we are supporting 3 main sample delivery methods for the users. But as I said before, we are also have the capability to accommodate user-developed sample delivery methods. So the first one is fixed target, either on foils or sheet-on-sheet support of silicon chip. So this is a foil system which is actually what we normally use for sample pre-characterization and for native data collection, because out of this support, which is more or less the size of 1 centimeter by 1.5 centimeter, you just need to load between 3 and 5 microliter of crystal slurry. Typically, we collect in S-shaped data scan, as we will do as I show here. And as of course, since we are producing a pulse every a bit more than 4 milliseconds, every time that we exposed, there is a certain spacing between the different exposed area. Typically, we use a 20 by 20 spacing, so that means both the horizontal and the vertical spacing are 20 micron. So that means that we have an exposure time of the largest 90 microsecond in one point here, and the next shot is going to be given 20 micron aside. And this is something that we found that is quite safe margin in order to avoid damage being propagated across the crystals. Of course, if we reduce that spacing by, let's say, down to 5 micron, then we start seeing cross-contamination from the tails of the beam. Out of one of these support, with the 20 by 20 micron spacing, we can collect 240,000 images, which of course, as you see, that even if we have like hit rate as low as 10 or 5%, that is also already more than 10,000 images being collected. And then, yeah, as I said, we can also accommodate user design support. Actually, all this possible geometry that you see, they are just defined in a JSON file. and this is actually it's a video. This is like on a broken chip, but this is you see during the acquisition being performed on a single city block, in this case of a silicon chip. And this is, of course, is how it looks like the crystal slurry when we mount it on the foils. The other sample delivery system that we support are high viscosity extruders and also the Ceralix injector that's been developed at Gothenburg University. Of course, this is much more used for crystals that they grow in LCP, but we can also provide and other carrier media like hydroxycyl cellulose and grease. On the B line in the lab, we have also an offline batch which can be used to do a pre-characterization of the flowing of the sample. But again, I mean, we have a sort of very generic frame for support, and we can accommodate different kinds of devices. In fact, that we have done recently an experiment, for example, with Cara, with their device, but we have done also some experiment with Takashi Tomizaki from PSI by using the acoustic levitator. The other sample delivery methods that we routinely use is a tape drive system. So we have adapted in a collaboration the tape drive that has been developed by the Lübeck Technical University. And we have developed a two-channel mixing nozzle, which has been inspired by what was done at CFEL by CFEL guys, by Dominic, with their tape drive system. And this is basically works like, I like to always describe like a fountain pen. Here you see that is the tray of the crystal being deposited, and we keep pumping the two. In one channel, the straight one, we pump the crystal slurry, and in the second one, that is just, let's say, coaxial to that, the ligand. And by offsetting the position where we deposit to the position where the beam is, we can perform different delay time. And this is see an example. This is one of our in-house project of the electron density of the in this case, the crystals were, they need two substrate in order to produce a reaction. So the crystal slurry was produced with one of the substrate, and then the other molecule was added. And this is the apo structure with a FO minus FC map. This is at the beginning of the reaction, and this is at the end, 2 seconds down on the tape drive when we add the second molecule. And this is a very highly requested by users. Of course, it's let's say more tricky operation than the foils, but what we saw is that it can be very versatile based on the sample. So a bit of structure quality and what could be the effect of radiation damage. So of course, when we started, we were not sure what was going to be completely what was going to be the effect of having such a strong X-ray pulses, which was clearly a few order of magnitude shorter than what was done at the third generation microfocus beamline, but still many order of magnitude longer than the paradigm of the diffraction before destruction at free electron laser. So we have collected data on foils just to try to identify if there was some damage being produced. And also, so we saw that basically, and this is you see with monitoring disulfide bond, and this is an OMIP map. By reducing the spacing between the shots when collecting on foils, and we see that this disulfide bonds are preserved even when going down to 10 micron spacing. This is not anymore the case when we further reuse that. And we also monitor for global damage effect by following the possible intensity decay by using different spacing, and the sort of diffraction intensities is preserved no matter what kind of spacing that we use. And this is, for example, how it looks like. And this is a myoglobin in complex with the water molecule, and we don't see even by using a very bright 10 microsecond pulses the leaving of the water from the active site. So as I said, we have in the slowest mode we have a 90 microsecond pulses, which is produced a bit more every 4 microsecond. This, of course, as compared with doing this kind of similar experiment with the continuous beam at third generation synchrotron, has also the advantage of maximizing what is the signal to noise. Because if the crystal is as small, not to stay in the beam for the whole exposure time because of fast translation on the files or because of the injector, of course, you will be recording with longer exposure a lot of background. So we have calculated for the different spacing that we have between two different X-ray pulses of how much the sample would move when we're collecting foils. And since basically since our clock is produced by this repetition rate, which is the rate at which the pulsar produces, when we change the spacing, what happens is that, practically speaking, we change the speed. So for larger spacing, we have higher speed of the translation. So in the worst case scenario, when we use the 90 microsecond pulses, you see that when we have a spacing of 10 micron, the crystal moves in the beam by less than, much less than a micron. So making sure that the crystal stays, which is usually much smaller than, which is smaller than the beam size and smaller than the crystal size that we typically measure, making sure that the crystal is in the beam for the whole exposure. But even in the worst case scenario, when we use the silicon chip, the Oxford one, in which the spacing is 125 micron, which is defined by the geometry of the chip. Even in that case, the movement is by less than 3 microns, so it's that it's smaller than the size of the aperture that you had at the end of the funnel. And in a similar way, we have calculated what is the jet speed in the experiment that we have done with HV, and I think this was with hydroxyacetylcellulose cellulose. Even in that case, with the 90 microsecond pulses, the crystal was shifted by less than a micron. Then we have tried to see how much, or at least, let's say, how many few frames we need in order to get a complete structural information for ligated structure. And we have performed as a test case on the lysozyme in complex with GalNAc. In this case, we have collected data on the Oxford silicon chip. And then we did a sort of data titration by analyzing the FO minus FO isomorphous map. And you can see that basically with at least as little as 2,000-3,000 images probably, it's enough to have a complete and purely interpretable isomorphous difference map, which of course becomes more interesting when we apply to some more, let's say, challenging example. And this was the structure of the GPCR, the A2A adenosine receptor, which has been crystallized, and this is a collaboration with a group of Guillaume Lebon from the CNRS at Montpellier, in complex with the istradefylline Parkinson drug. So this has been crystallized in LCP, and we show, well, in the paper, that we could obtain a full data set up to 2.5 angstrom just by using 50 microliter in total of LCP bolus, and not collecting as would have been, let's say, more obvious for protein that crystallized in LCP, not collecting on a high viscosity extruder, but by gently dispensing and spreading the LCP bolus on foils. And here you see this is a FO minus FC map because we didn't have the hollow the HAPO structure. But you can see that the drug is fully resolved with just 1,000 or even say 2,000 images. The FO minus FC fully reveals the presence of the molecule bound in the active site, which can be placed and refined. So a bit of data acquisition on data analysis. As I said, we operate with Jungfrau 4M, and for which is operated through ESRF developed data acquisition pipeline and backend, which is called Lima 2. So with Lima 2, we do on the fly the geometrical correction of the images and the pedestal correction, because Jungfrau being an automatic gain switching integrating detector, it needs to have the pedestal corrected for the 3 different level of gains. But most importantly, at least from a user point of view, is the fact that as part of data acquisition, we performed on the fly peak identification. And this is what you see. Basically, this is what the user sees. This is just a screenshot of the line where they are collecting on the foil. So every time that there is a frame that contains peaks, this is recorded, and then similar to what is done in I think Cheetah and was done in NanoPixel, all the frames that they contain diffraction are accumulated to create a virtual diffraction pattern that you can see here more in detail. So the user have an estimate from that of how much the crystals are, up to which resolution the crystals are diffracting, and also what is the heat rate that they can expect from the crystals from the data collection. All this information is also stored in the metadata of the HDF5 files. So along with the data, the users they contain, and this is one HDF5 files container of 1,000 frames. You know, for each of the frame, how many peaks have been identified. In order to cope with the data throughput, because at that repetition rate, clearly we have a really data deluge. We discard, but this is an option in the data acquisition software. We discard all the frames that do not contain diffraction, but you cannot see here because it's in the back. We also perform an accumulated virtual diffraction powder, virtual powder diffraction, also from all the images that are not hits as a sanity check. In addition to ligand mixing, we are also giving the possibility to do light activation. As I mentioned before, we are commissioning a nanosecond laser, which can, and we have also equipped the beamline with different high power laser diodes, which provide digital modulation, and we have a set of 5 different fixed wavelength in order to cover all the spectra, or at least a wide spectral range. We are at the moment focusing the laser with an external optics with the grazing angle. And again, with in collaboration with the MBL, we are developing a laser injection system which uses the sample view microscope so that we can focus at a sample position. And here you see, for example, it's yet again, it's a screenshot of data acquisition as it performed on the laser by using the silicon chip. Of course, the hatch was in the dark, so there is not much to see. So I'm getting close to my conclusion. So this is basically the team that operates the beeline. Julian was a postdoc on the beeline until last September, and then he left. So at the moment we are a bit running everywhere because we're just 3 supporting user operation of the beeline. So this is Sam, a postdoc that is also doing a lot of radiation damages analysis by coming that I can use for this bright beams. And Shibom is the my equivalent scientist that works for the MBL that provides support and development for the beamline. And of course, there are a lot of people to thank, and all the people that they participated to the development of the software and the beeline design and the beeline commissioning. And I think I'm done for now.